Bienvenidos, Ushamadid, and welcome UMGC learners for CMIT-455 Section 6380, which is the Cisco Networking Academy CCNP ENCOR version 8 curriculum. This course is the spring 2021 semester, and this activity is going to be a deep dive into Packet Tracer Activity 9.2.2, where we're going to configure OSPFv2 advanced features. Now, when I say OSPFv2, remember that that implies IPv4 and IPv4 only. And so it's OSPFv2, we're using IPv4, and we're going to be taking a look at some advanced features, and we're going to go well beyond the features that are listed here. We're going to be talking about the auto cost reference bandwidth setting. We're going to be taking another look at passive interfaces, and we're going to break down in detail exactly how you calculate the cost for a route in an OSPF network. So let's dive in and take a look at the activity as it is currently laid out. You can see we have a triangle of routers 1, 2, and 3, and then we have our internet web server, and we have 3 LAN segments that hang off of these routers. So we've got our addressing table here to the right. We're going to go ahead and dive into the activity right away. Now, they want us to test connectivity between all devices before modifying anything. So let's make sure that the PCs, and I'll pull these down here. I had the routers up, but not the PCs yet. And let's test, can I ping to 172.16.2.2, and that is going to be PC2. And again, we probably have the address resolution protocol at play here, right? We had to send out an ARP request to try to figure out what is the layer 2 MAC address for, what's the layer 2 address, the MAC address for my default gateway. And that worked just fine. And now we're going to do PC3, which is 192.168.1.2. And we should be able to hit PC3 without any issues. Now, one of the reasons I'm going to be adding in a lot of additional information to this activity, as you can see, we're not really doing a ton of advanced OSPF features. Now, I know that some of this is going to be due to the limitations of Packet Tracer. Again, Packet Tracer is software, and it is great software, but it is limited in the features, the iOS and iOS XE feature sets that it supports. So let's dive in here. It wants us to adjust the hello and dead timers between router 1 and router 2. Now, a quick note on this. What are the defaults for a point-to-point network type, and how could we see that? Well, you might be thinking, let's just say show IP OSPF neighbors, that should tell me. Well, that's going to give you the dead timer, and you might be able to back into a response here, seeing that it goes down to 30, and then it comes all the way back up, and you'll never see it at 40. I have never seen the dead timer at 40, which is the default on broadcast and point-to-point networks. Now, if it goes down to right around 30 and then pops back up to 39, which again, it's really going to 40, but then we come down to 39 immediately. So it's 10 seconds. So you might be able to work it out like that. However, show IP OSPF interfaces, right? Remember, this command is going to give us a very nice look at all of the interfaces. And take a look here on a broadcast network type, such as Ethernet, which you'll hear me refer to a lot as broadcast multi-access, right? That is Ethernet. And take a look at our default settings for the hello timer and the dead timer. It's 10 seconds for the hello packets. And then if I haven't received 4 of those within the sending time, again, assuming that they stopped coming at the 40-second mark, we would then take the adjacency down. right? And the adjacency would be broken. Because remember, the hello packets are used not only for neighbor discovery, they're used for neighbor maintenance and keeping that adjacency alive and well. And that is the purpose of that OSPF hello packet. Now, there's a lot of information in that packet for a lot of other things, but it's all about neighbor discovery, neighbor acquisition, and neighbor maintenance, keeping that relationship with your neighbor up and alive and healthy. And then the dead timer, again, would be 4 times the hello timer by default. Now, when we look at a point-to-point interface, or I'm sorry, point-to-point network type, we can see that the hello timer is 10 and the dead timer is 40. So by default, both broadcast network types and point-to-point network types have the same hello and dead timer default values. Now, what we're going to do here is we're going to be changing these. Now, it could be that there's some delay. And again, the use case for, well, wait a second, the defaults seem pretty solid. Why would I want to change the defaults? 99% of the time, you're not going to change the defaults. Now, I know what you're probably thinking, because years ago, this is what I used to think. Well, what if I'm worried that the adjacency goes down, but I don't recognize that it's gone down fast enough, right? Because think about this. If at the 39-second mark in the dead timer interval, some transit issue happens to where I stop receiving hello packets, it could be up to 40 seconds, or let's say 39 seconds, before the adjacency is taken down. And in that 39 to 40 seconds, I might have traffic black holing. Now, in terms of convergence, that is not a flap. That is an outage, right? And so the thinking that a lot of learners have when they look at the hello interval and they look at the dead interval is they think to themselves, I'm going to shrink that down to the smallest possible values that I can use. And while you could do that, that is not the recommended way to do it. I'm not sure if it's covered in this course. I don't believe that it is. But the true way that you would deal with this is with a protocol called BFD, for bidirectional forwarding detection. And BFD will let you run it down into the millisecond range in terms of these very lightweight BFD packets that will go back and forth over the link to determine whether that link is up or down. And so tweaking your hello and dead interval is not really what you would do. Again, they show you this for a reason, not only for testing purposes, right? But they show this to you for a reason because maybe we've got a lot of latency on the link. Maybe we're okay if we're waiting for 40 seconds for OSPF to determine that the adjacency is down, that's not going to be an issue. In cases where that is not true, you would use bidirectional forwarding detection. In cases where you're okay with this, you typically leave this with the values that are set. Again, I was told a long time ago that there's a reason Cisco set default values to be the defaults. And it's because Cisco is pretty smart about Cisco, right? And so for you to get in there and start mucking around with the default values, you better have a very good reason to do that. So let's go ahead and let's address what they're asking us to address. And that's going to be the hello interval and the dead interval. Well, how do we do that? We have to go into the interface specifically that we want to tweak these values for. And again, we're talking about the serial 000 interface, which is right here on router 1 connected to router 2. Now, I want you to watch something. If I say IP OSPF hello interval, I can shrink that down to 1 second. Pretty quick, right? So, and by default, it's going to be the dead interval is going to be 4 times the hello interval. So the dead interval would change to 4. Or would we have to change it? Well, let's do this. I'm going to say IP OSPF hello interval 1. Then we're going to say IP OSPF interface. IP OSPF show IP OSPF interface. Do show IP OSPF interface. And take a look at what's happened on the serial 00 interface. The hello interval has changed, but the dead interval has not. So now we're going to have to change it. Now remember, that 39 seconds I was talking about, that is counting down right now because there are two values, or there are values that need to match between neighbors. And I'm going to make this 60. And if those don't match, then those neighbors are going to go down. And so you can see we've just lost our adjacency with router 2. So let's set it to the intervals that they want. We'll say 15, and then we'll say dead interval 60. And that was what they were looking for. Again, could I say IP OSPF hello interval 15 and then turn around and say, I only want to miss 2 packets before this adjacency goes down? You certainly could. And if I said do show IP OSPF interface, we can see that on serial 000, and I apologize, we just didn't go far enough there. You can see that the hello is 15 and the dead is now 30. Now take a look at the wait time. The wait time changed to match the dead interval. Is that what happened there? Well, we can easily find that out. Let's change this to 45 to say that if we miss 3 hello packets, the adjacency is going to go down. And lo and behold, the wait time changes to match the dead time. Now, I want to take a step back here to the hello and the dead interval. Remember, by default, the dead interval is going to be 4 times that hello interval. If they don't match between neighbors, the adjacency is not going to come up. And if I change them after the adjacency is up, the adjacency will go down. And we just saw that right up here, is that I had tweaked the hello interval to 1, 30, or however, approximately 40 seconds went by, and we noticed there's a mismatch there, and the adjacency goes down. And so you can see if I was to say do show IP OSPF neighbor, that we don't have at this point an adjacency with router 2 out the serial 000 interface, right? This is with router 3. And again, what do you also see here? Yeah, you better know that that IP address is somehow associated with router 3. That is the router ID for router 3. So in a larger environment, come up with a better router ID convention, right? And if you ask me, that would be an advanced feature that we would want to configure in our environment. All right, so what I want to show you now is that this is what happens on Packet Tracer. I'm able to manipulate the hello interval and the dead interval individually so that they don't, I can't depend on the fact that if I say IP OSPF hello interval 15, that's going to be 60, right? You've seen that when I said IP OSPF hello interval 15, that stayed at 40 until I changed it to 60. So let's set these to the intervals that they're supposed to be set to, right? And again, we're going to get points for that. So if you're watching the points, percentages that are going up, you can see that we've got this set. Now, how would I check that? Yeah, just simply say do show IP OSPF interface. Come down to that interface and see, all right, what's my hello interval? What's my dead interval? And then the wait is going to match the dead. Now, that is on Packet Tracer. If I come over, we're going to come to that in just a second. If I come over to real Cisco routers, and so this is a 2811 Cisco router running 15x code. If I was to go in and create a quick configuration here and just say router OSPF 10 and then say network, and we'll do quad 0. So we're going to turn OSPF on all interfaces on this router in area 0. And now I'm going to bring up an interface. So we'll go into serial 000. I'll say IP address 10 dot router 8 and router 9 are involved here, and this is router 8, and we'll make it a /24. We'll say no shut. Oops, sorry. Wanted that to be 255, 0. Sorry about that. Oh, and so we already have some configuration on here. Do show IP interface brief. Sorry about that. Okay, my apologies. I didn't realize we had all this configuration on here. So we have what we need right now. So if I was to say do show IP OSPF interface, what we would see here for that fast Ethernet 00, and there's the serial links, but we're going to be interested in the fast Ethernet 00, and I guess we'll take a look here at .816. You can see that its network type is broadcast, and again, for all broadcast network types, those are going to be the defaults. Now, what if I go into interface fast Ethernet 00.816, and I say IP OSPF hello interval, and again, I can shrink this down. Let me say 5 seconds. So now if I say do show IP OSPF interface, and we come down to 816, take a look at what happened. What happens on real Cisco iOS? On the real Cisco iOS, and again, this is an older, it's a 15.1, so on 15.7 code, you're definitely going to see behavior similar to this, and that is that when you change the hello interval on real Cisco iOS, the dead interval will change to be 4 times the hello interval that you set. In other words, I don't have to say IP OSPF hello interval and set it to 4 times the dead interval and set it to 4 times the hello interval. If that was what I was going to do, all I would have to do is set the hello interval, and by default, iOS will say, well, he set the hello interval to 5. We're going to go ahead and do our default behavior. We're going to set the dead interval and set the wait interval to match the dead interval to 4 times the hello interval. And that's exactly the behavior that you're going to see. Now, I understand why in the activity. Again, there's a lot of times, don't feel that I'm nitpicking on certain things in these packet tracer activities, because I know why they're in there. You have to know how to set that dead interval. You have to understand that you can set it to something other than 4 times the hello interval, right? But again, I really like to point out what you're going to see on real Cisco iOS. Now, the question becomes, well, what if I set the dead interval to something different? Does that force the hello interval to be 4 times or to be a divisor of 4 of the dead interval? In other words, if I set the hello interval to if I set the dead interval to 120, if I divide that by 4, is it going to set the hello interval to 30? Well, let's check it out here. Do show IP OSPF interface. We come down to 0, fast Ethernet 00.816, and no, it does not. But the wait timer will match the dead timer. You see how that happens. So, in summary, if I set the hello interval on real Cisco iOS, by default, iOS will set the dead timer to 4 times the hello interval. If I set the hello interval manually, I can independently change the dead interval from being 4 times the hello interval. And the wait timer is going to match that dead interval, the dead interval value every single time, right? And so you can see that we've got this set up very nicely. And so you might be asking yourself, well, wait a second, I should be able to tweak the wait timer. And as you can see here, right, there is no IP OSPF hello interval or dead interval command for the wait interval, right? For that wait interval. And again, that wait interval is going to get set to 4 times the dead interval. To 4 times the hello interval, which the dead interval will also be 4 times that value. So remember that as you work with real Cisco IOS. So we've got that done. We saw the adjacency is not going to come up. We're going to come back over to router 2 because in order to fix that, we need to go into interface serial 001 on router 2. Hold on, no, I'm sorry, serial 000 on router 2. And we're going to say IP OSPF hello interval 15 and IP OSPF dead interval 60. Again, remember, on real iOS, it would already be 60. And the wait timer would already be 60 because I had set the hello interval to 15. All right, so now, in about 10 seconds here, we're going to see, I'm sorry, in about 15 seconds, we're going to see that the adjacency comes back up. I said 10, thinking the hello packet interval was 10, but we just changed it to 15. So, there we go. We now have that adjacency back up. Show IP OSPF neighbors. And you can see we now have both of our adjacencies on router 2 with router 1 and router 3. And that has actually taken us all the way up to 80%. Now we're going to get down to a more interesting conversation. Again, the defaults here with the hello and dead intervals are typically not manipulated. But know how to do that because this will come up. And know, more importantly, that if the hello interval doesn't match, the adjacency between two routers, if not already established, will not come up. Excuse me. And if already established and you mismatch them, the hello interval, the adjacency will go down after the dead timer expires. And you can see now here as well, right before we transition, that dead timer, look at that. It's going to go to 60 and it's going to start to count down, right? The countdown to extinction here. And it's going to get down to right around 45, right? That's that 15-second mark for the hello packets. And as soon as it receives that hello packet, boom, it resets the timer back up to 60 again. This is the maintenance, the upkeep of that neighbor relationship. That's another function of hello packets in OSPF. So now we're down to step 3. We're going to adjust the bandwidth setting on router 1. Now, this is extremely important. And I'm going to make some statements here that I'm going to caveat because you have to caveat these statements. You can see that we have serial links running between these routers. If I was to say, do show interface serial 000, not show run interface, but show interface, we can see the default bandwidth for a serial interface is 1,544 kilobits per second. In other words, 1.544 megabits per second. That is the default bandwidth. Now, on a serial connection, if you're connected to a telco provider, you might be connecting to a MUX, M-U-X, a MUX, meaning you may be getting a fraction of that 1.544 megabits per second, or 1,544 kilobits per second. You might be getting a fraction of that. You could be getting 64 kilobits a second. You could be getting 128, 256, 512, 768, or the full 1544. Now, and these are routers that are connected back to back, right? So they would enjoy the entire 1.544 megabits per second. Again, if you're connected to a telco provider and it's a MUX, you can order, and again, these are going away. These are sort of legacy type serial connections that we're talking about when I'm saying, a 64 kilobit fractional link or a 256 or 512. Do they exist? They absolutely do. I still have multiple fractional circuits that I work with both Verizon and AT&T for backup links to 1 gigabit a second MPLS L3 VPN connections that we deal with an in-house service provider for. So, but again, you'll see these in environments sometimes. And so this is an important conversation to have. When OSPF is making its routing decisions, it's making its routing decisions based on cost. what is the cost for me, router 1, to get to some network maybe over here behind router 2? So let's take a look at where would we see that cost. Well, let's say show IP route, or do show IP route. So if I want to know what my cost is to reach this network segment, as router 1, again, we're talking about it as me, router 1, I need to determine, do I want to go this way or do I want to go this way? Now, from looking at the diagram here, it's kind of a moot point, right? You can obviously see that, well, if I go to router 2, I'm there, right? But maybe this is 64 kilobits a second. And this is the full 1.544 megabits per second. Or I'll put it in, it's 1,544 kilobits per second. And maybe this is also the full 1,544 kilobits per second. So maybe it's faster, there's more available bandwidth taking the southbound route down here and going around a router 2 through router 3. These are the decisions that the dynamic routing protocols like OSPF and EIGRP and IS to IS have to make. That's what Dijkstra's shortest path first algorithm, the SPF algorithm, is all about. It's about building the shortest path tree. This graph that I keep mentioning, right? What graph am I going to build that has all of the shortest pathways to get to these different leafs on the graph or nodes on the graph? So we look at this network here, 172.16.20/24. Do I have an OSPF learned route? I do. There it is right there, the O, and it is an intra area route. There is no OIA here. Now, if I would have originated that network with a network statement similar to network, and this is under the OSPF global config section, had I said network 172.16.2.0 space 000.255 for the wildcard mask, area 2, we would see this as an OIA. But we don't. It was originated in area 0. We see it as an intra, not an inter area OSPF route. And there is the metric. You can also see we have the metric for the 192.168.1 over here behind router 3. And now this is where the magic happens with respect to the metric calculation. So I can see that it's 65 as my cost. That is my cumulative cost, meaning that is a representation of all of the outgoing interfaces through which I would have to transit to reach this network. And you can see via, so who is my next hop? Well, the next hop is the 172.16.3.2. And that is out what local interface? Serial 000. So we know right now this is my shortest, lowest cost. When you say shortest path in OSPF, you are really implying lowest cost, because lower is always going to be better from a path selection process with OSPF. Lower is always better. So 65 is better than the cost of going this direction. And so now let's clear the screen here, and I'm going to show you how to determine, how is OSPF making that calculation? Where is 65? I mean, what in the world does that mean? How is that being determined? So if we know that I go out this interface, remember, it's outbound interfaces. I'm going to hammer this point in because the confusion would be with learners, and this is what you'll see, is they look at the cost of this link. From router 1's perspective, if I go out this link, what's the cost? They then look at the cost of that link. That is not an outgoing link. That is not a link that I'm adding to the cost. The cost is outgoing links. And so if this is the outgoing path to get to that network segment, not specifically that PC, but just this network, there are only 2 outgoing interfaces from router 1's perspective. It's the serial 000 interface right here and the gig 0, and I'm assuming that's gig 00 there. I can't see router 2, but I'm assuming that's gig 00 here. So we're going to say gig 00 is an outgoing interface, and serial 000 is an outgoing interface. Interfaces out which I have to go to get to that network, not interfaces into which I go. I'm going out that interface to get there. I'm coming in this interface and going out. We want the outbound interfaces when we're calculating this magical metric number of 65. And here's how you can do that. I would simply take a look at those 2 outbound interfaces by saying, do show IP OSPF interface. Let's take a look at serial 000. What is the cost of this interface? And there it is. At the end of the line that has the network type, we have the cost. Now, will it allow me to say I'm not going to do the include to try to get it out of there, but because I don't think it's going to work, because I just remember it didn't work earlier for another command that I wanted. So we've got this cost here, right? The cost is 64. So now your question should be, okay, well, that's great. So then are all serial links going to have a cost of 64? And the answer to that is maybe. It depends. It depends on the bandwidth of that interface. And so now you're probably asking yourself, okay, well, wait a second. You just said that the bandwidth is all the same. Well, I can change the bandwidth. And here's the use case. And for me, we're talking about layer 3 traffic engineering. We're going to try to manipulate the flow of traffic at layer 3 using the OSPF routing protocol. And to do that, we could manipulate the bandwidth. However, the only time that you should be manipulating and performing layer 3 traffic engineering in an enterprise environment using the bandwidth is you really shouldn't. The only time the bandwidth should be used is when you're putting that setting on an interface to accurately reflect the bandwidth of that interface. So, what I'm saying there is, if you have a fractional serial link, a fractional link to a telco that is 64 kilobits, or that is 256K, or 512K, or 768, that is when you put the bandwidth command on the serial interface, is when it reflects the actual bandwidth that that interface is capable of. If you're simply doing layer 3 traffic engineering, you would not be manipulating the flow of traffic with the bandwidth statement. Especially when you're talking about OSPF, you would use IP OSPF cost. You can go onto the interface and directly manipulate the cost. And you should now be asking, well, why is that? Why are they showing me how to use the bandwidth statement here? They're showing you how to use it because in environments where you have fractional serial links, like the 256, the 512, the 768, you definitely want to go in there and set the bandwidth statement. So you might be asking yourself, why are you telling me to only do it when the link to reflect the actual link bandwidth and not to do traffic engineering? And here's why. What if in this environment, I'm also running EIGRP? What if I'm also running IS to IS? And more specifically, EIGRP, right? What if I'm running EIGRP here? And I go in and I start changing the bandwidth settings on interfaces to manipulate the flow of OSPF traffic at layer 3. Not because the links are that speed in bandwidth, but because I'm trying to do a bunch of layer 3 traffic engineering using bandwidth. On links, assume those are gigabit Ethernet links. And I'm like, oh, okay, well, if I set the bandwidth to 64, that'll definitely impact OSPF. And the answer is yes, it will, but it's also going to impact other things. If you're using quality of service, you have just impacted that. If you're using EIGRP across that link, you have just impacted that. And so that is why you do not use the bandwidth statement to perform layer 3 traffic engineering. You use the bandwidth statement and apply it on interfaces to accurately reflect the bandwidth of that link. And so they're showing you how to do that here. Again, we're going to assume that this is a 64 kilobit per second link here. But they're showing you how to manipulate OSPF traffic flow. Again, the real way to do that is with the IP OSPF cost command so that you don't impact other things like quality of service, like EIGRP. Now, again, if you're only running OSPF here, sure, you could get away with this if you're not running EIGRP, if you're not running quality of service. But keep in mind that sure, you could do it this way. However, should you? The traffic engineering portion, not the setting the bandwidth on the interface to what it actually is, if it was fractional, but should you be using the bandwidth statement to perform traffic engineering with OSPF? And the answer is probably not. The purist is going to tell you, no, use the IP OSPF cost statement if that's what you want to do. So we're going to set the bandwidth statement here. I'm sorry, let me finish here. So we left off with out that interface, it's a cost of 64. What about router 2? Well, if I say show IP OSPF interfaces, we're going to see that gigabit 00 link. That's our link, and it is that link out to the 172. So I was just checking to make sure that that was the right link. And what is the cost? The cost is 1. So if the cost is 64 for, and again, remember for router 1 and anything going through router 1 here that's going to go that direction to get to this network, the cost of this interface is 64. The cost of that interface is 1. And so 64 plus 1 gives us 65. We look at the routing table again here on router 1. What did it say my cost to reach that 172.16.2 network's going to be? It's going to be 65. And the cost is the same to come out that interface and then this interface on router 3 to get to the 192.168.1. It's going to be 64 and then it's going to be 1. So now you should be asking the question, well, where are you coming up with those values? Is that, are those hard-coded somewhere? And the answer is there's an equation that gets used to calculate what the cost is with OSPF, and it's all based on the auto cost reference bandwidth. There's a reference bandwidth setting. Again, think of it as a starting point or a benchmark setting that all routers running OSPF, all Cisco routers running OSPF start out and they say, I'm going to be calculating the cost for all of the interfaces that are running OSPF based on the following equation. It's 10 to the 8 divided by the interface speed in bits per second. So 10 to the 8, which is 100 million, right? Because it's going to be 8 zeros here. 1, 2, 3, comma, 1, 2, 3, divided by the speed of the interface in bits per second. Well, let me prove that to you. Let's just not say that and assume that that's true. Let's pull out the trusty calculator and try to get it away from all of the writing. So this was 1,544 kilobits. Remember, that is significant because the equation, we're interested in bits per second, not kilobits per second. So if I said 1,544 kilobits per second, I would have to say 1, 2, 3 to get to bits per second. So what do we have here? 1,544,000. So if I take 10 to the 8, 1, 2, 3, 4, 5, 6, 7, 8, and divide that by 1,544,123, what do we get? 64.76. So here's how OSPF deals with this fractional leftover. It always rounds down. There will always be whole numbers. You will never see a cost in OSPF of 64.76683 whatever. It's going to round down. And so the cost is 64. And so OSPF uses this 10 to the 8 number, which, if you've been thinking out loud here, isn't that 100 megabits per second? And you would be correct. 10 to the 8, this 100 million is 100 million bits per second. And that's an easy way to remember what the default auto cost reference bandwidth setting is. And so this is how OSPF calculates the cost out an interface. It's using a baseline value of 100 megabits per second, 100 million, 10 to the 8. That is the default value that is used in calculating the cost out an interface divided by the bits per second for the speed of the interface. And so let's go ahead and confirm that with the gigabit internet, the gigabit 00 interface here. And so if 100 megabits is 100 million and a gigabit is 100 megabits, and this is where some of the older books, I'll actually pull this chart up that we have here, and this is a good time to take a look at this chart. And this comes out of an older text, but you can see here, if the reference bandwidth in bits per second is 10 to the 8, right, this 100 million that we have all the way down here, I just need to convert the interface into bits per second and then do the division. And that's where I'm going to get the costs. So for an Ethernet, and again, these are, you're probably never going to see these anymore, a 10 megabit per second interface. Fast Ethernet maybe on some legacy routers like the ISRG ones that I use in my lab, the 2800s, the 1800s, those are all 100 megabits per second on those interfaces by default. And so the cost would be 1. A gigabit Ethernet interface, you can see here, is 1 billion, right? Gigabits is 1 billion bits per second. And if you divide 100 million by that, you get 1. Now you'll notice that even with 10 gigabits, it's 1. And herein lies the problem in modern day networks. OSPF, again, was created late 80s, right? When 100 megabits per second was bleeding edge in terms of interface speed. And so this is why that value was chosen as the reference bandwidth, right? The baseline on which we're going to calculate the cost for OSPF through all other interface speeds. Here's a fractional 128 kilobits per second. Cost of 781. Here's 64 kilobits per second, cost of 1562, which we're getting ready to see here shortly. But we need to understand the problem with the default auto cost reference bandwidth of 100 megabits per second. And that is that any interface speed 100 megabits per second or faster, 1 gigabit per second, 10 gigabits per second, 40 gigabits per second, which is common today in data centers, 100 gigabits per second. Not so common, but it's there. We're there. All of those would have the exact same cost. And so what I would really be saying by leaving the reference bandwidth setting at 100 megabits a second is that 100 megabit per second fast Ethernet interface should be treated the same as and have the same cost as a 100 gigabit per second interface. And that statement alone should have you scratching your head saying, there is no way I would want that. There's no way I would want a 100 megabit per second interface to be treated the same in terms of preference from OSPF's viewpoint as a 100 gigabit per second interface. There's no way you would want that to happen. And again, I say that, facetiously. Sure, I'm sure there's a corner case where you could come up and say, oh no, here's where the fast Ethernet interface would be preferred. But I'm saying, in general, if you looked at that statement on its face, that we should treat with OSPF's point of view, from OSPF's perspective, I would want to treat a 100 megabit per second interface the same as a 100 gigabit per second interface. I would say right there, you're insane. There's no way you're going to want to do that. And so that's where we have an optimization that should be put into play, and that is the manipulation of the auto cost reference bandwidth, which we're going to get to in a second. Again, this is showing you how OSPF, using the default auto cost reference bandwidth setting, would calculate the cost for different interface speeds that you may run into. So now let's transition back to the activity. And let's complete this activity with what they're asking us to do. Let's go into int serial 000, and let me, again, do show IP interface brief. Let me make sure here. It says it, but I just want to make sure 16.3.1. So that is it. And I'm going to say bandwidth 64. Now, how can I confirm that that actually took place, right? Do show interface serial 00. And remember, the extra zeros are free here. iOS isn't going to punish me for that, right? It's going to do what I asked it to do. The zeros are free. And you can see, there it is. The bandwidth has been set to 64 kilobits per second. So what does that tell you? Well, that tells you that that command, by default, or I should say, is going to force you to put in the bandwidth that you desire in kilobits per second. And the reason that it's set like that, think about what we've been talking about here. Why would it be that the default is in kilobits per second? Because I'm typically going to be talking about setting that statement on an interface that is a serial interface that's probably being run in a fractional sense. In another way to say that is, I'm probably going to be limiting a serial interface because it's fractional to kilobits per second, to 64, to 128, to 512, to 768. It's going to be some fractional form in kilobits for a serial interface. That's the type of interface that command is going to be placed on. And it's on that type of interface, a fractional interface, is the only place that you should be putting that command in an OSPF context to accurately reflect the bandwidth speed of the link. Here we're doing it again. We're manipulating the bandwidth setting on this interface, but we're doing it in sort of an underhanded fashion to try to change the flow of traffic to make this interface, look worse from an OSPF perspective. And you might be saying, well, wait, you said lower is better. Well, lower in cost is better. There's an inverse relationship between the bandwidth of the interface and the cost. And here is what I mean by that. The higher, and I'll just put high, The higher the bandwidth on the interface means the faster the interface means the lower the cost. It's an inverse relationship. The higher the bandwidth, the lower the cost. The lower the bandwidth, like we just saw and we're going to see here shortly, the higher the cost. And from OSPF's perspective, I'll just say the higher the cost. And from OSPF's perspective, a higher cost is bad. When I'm making a decision picking between two links, I want the lower cost because the lower cost link implies higher bandwidth. It's an inverse relationship. So now that we've changed it to 64 here on router 1, let's take a look at our cost. Do show IP OSPF interface. What is the cost now of that serial 000 link? OSPF said, give me my calculator, OSPF said my default auto cost, the auto, right? It's auto magically calculating my cost based on a reference bandwidth of 10 to the 8, 1, 2, 3, 4, 5, 6, and I already had 2 in there for 7 and 8. So 10 to the 8 divided by the speed of the interface in bits per second. Remember, these are bits per second when performing the calculation. So it's 100 million for 100 megabits per second divided by, not the cost. Remember, we set it to 64 thousand. 64,000 bits per second is 64 kilobits per second. And what do I get? 1562. If I set it to, what's a value? We don't have a value over here of what, 768? Yeah. So to prove to you that these aren't pre-canned, if I had auto cost 1, 2, 3, 4, 5, 6, 7, 8, 10 to the 8 divided by 768 1, 2, 3 zeros, my cost would be 130. How can I prove that to you? Well, let's come onto this interface and let's say bandwidth 768. And now let's say do show, and I can just up arrow, do show IP OSPF interface, cost of 130. That is how OSPF is calculating the cost on a per interface basis on which OSPF is running, right? This is from OSPF's perspective. Let me put that in there. And again, that gives us the 100%, but there's more to the conversation here. So that's how I calculate the cost. Now, do I only do it here because I'm thinking that we're talking about these outgoing interfaces? Well, yes. I'm sorry. You might think, yeah, okay, well, that's right. That's what I want to do. That's the path that I would want to take or that I would not want to take. But is that what we want to do? Because now we're saying that PC1, let's pull PC1 up and let's trace out to the 172.16.3, .2, and we'll go to PC2, .2.2. And let's see how we get there. So I go to the 117.16.11, that's my default gateway, and then I go to the 192.168.10.6. So this had the desired effect. Traffic is no longer going this way because we've lowered the bandwidth, meaning we have increased the cost to a higher value, meaning that it's cheaper for me, if I say do show IP route, it's cheaper for me to get to the 172.16.2.2 to now go over here and then up to router 2 and then over to PC2. Because the cost is 129 going the southbound route. What's the cost going the northbound route here? In other words, I come to router 1 and I head straight north. Well, I've got to go out that interface. Well, remember, do show IP OSPF interface. What is the cost? The cost of just that interface right now. For me to go out that interface, the cost is $15.62. So is it cheaper to go 1562 and then add 1 for the gig interface. So total of 1563. Is that lower? Is that better than the 64 to come out this interface, the 64 to come out that interface? That's 128. That gets me here. And then this interface is 100, add 1, makes it 129. So it's 129 from an OSPF cost perspective to go southbound and then northbound than it is to simply hit router 1 and come up to router 2 and come over here. Now, if we're looking at RIP, RIP is all about hop count. RIP is always going to come to router 1 and then go to router 2. It's fewer hops. And here's a great example of if this was a 64 kilobit link between router 1 and router 2, and we were running RIP, RIP is not very smart, right? By default, RIP is not very smart. RIP is going to say, well, I always come to router 1 and then go to router 2 because that's 1 hop. To go over here to router 3 and then to router 2, that's 2 hops. And 1 hop is better than 2 hops. RIP doesn't care about the bandwidth. And that's where you get into trouble with RIP. OSPF bases its decision on the bandwidth of the interface to arrive at a cost value, which we've seen how to calculate. And then that is how OSPF, in the shortest path first algorithm, create the shortest path tree. The graph showing you the nodes and the cost to get to that node, and then to hit the network, the leaf that might hang off that node, right? And so that is how OSPF is calculating all of these things. Now, back to this conversation. Do I go out router 3, and then I get up to router 2, and then I get to that the PC, right? So I get to the 172.16.3.2, which is going to be right here. 172.16.3.2 is this router, and then I go out that interface. Is that what I'm going to do, right, on the way back? Is that how the traffic is going to come back from PC2? Well, it's easy to check that, right? And that's the reason that in here it says on router 1, it says trace the path. Notice the path from PC1. Oh, and this is taking us out to the internet. The internet would be the same thing. I'm not, anything I've learned from router 2, any OSPF learned routes from router 2, including the default, as we saw right here in the routing table, the default says to go to router 3. That's the direction I should be going because the cost is better. It is lower going to router 3. And I will discuss that at a later time because you're probably saying, well, wait a second. You said in a previous video that OE2s always have a metric of 20. Why am I seeing the OE2, the default that's been originated into OSPF, with a cost of 1? We'll come back to that. So for right now, what if I'm on PC2 and I say, I want to go from PC2 to PC1? How is that traffic going to return to me? Well, sorry, let's say trace route to PC1, which is 172.16.1.2. All right, so I'm going to go to the 172.16.2.1 and then the 192.168.10.5 and then the 172.16.1.2. And so am I transiting this link over here? No, it's only 3 hops what I'm doing here. And so the return traffic, remember, OSPF is all about, from a cost perspective, the outgoing interfaces. And so if I'm on router 2, right, and remember, show IP route. If I'm on router 2 and I'm trying to get to the 172.16.1, and that's an OSPF learned route, why is router 2 saying go to router 1? How is it that router 2 doesn't know that router 1 thinks that that's a 64 kilobit per second interface? And it's because the cost is calculated from an interface perspective locally. That auto cost reference bandwidth on router 2 has no way to look over here on router 1 and say, well, what does router 1 think the cost of that interface is? And this is where, and I know that they're setting this conversation up for this internet connection, that you're going to come down this way and go this way. But watch what happens here. Right now, if we only set the 64 kilobits per second here, traffic between PC1 and PC2, specifically from PC2 to PC1, if in fact that was 64 kilobits a second, is taking a suboptimal path. We would want the traffic to come to router 2 and then over to router 3 and then through router 1. Just like we want the traffic from PC1 to come to router 1, then we want to avoid this link is what I'm saying, right? This serial link, this transit segment between router 1 and router 2, we want it to be avoided. But what's happening right now by only setting the true bandwidth of this interface right here is we're manipulating the route out to the internet for PC1, but traffic from PC2 is taking a suboptimal path if in fact this is 64 kilobits a second. So what would we want to do? Well, theoretically, realistically, we would come into interface serial 000 on router 2, and give me 1 second here. Let me make sure that that is, in fact, the 1632. It is. And we would want to say bandwidth in kilobits per second and set it to 64. You don't want to have mismatched bandwidth statements, and you don't want to have mismatched IP OSPF cost statements on opposite sides of the same segment, the same link, for the exact fact that I just showed you, for the exact reason I just showed you, is that PC1 is going to take the optimal path. It's going to come to router 1, 3, 2, and then out to PC2. But PC2, because router 2 has no idea that this is a 64 kilobit per second link, it thinks that the default setting on its interface, 1544 kilobits per second, that is what the speed of that interface is. And if that's the case, the auto cost reference bandwidth setting is going to honor that and say, okay, the cost is 64. And so for traffic that would be going out that interface to reach some network out this interface, that's the path it's going to go. And so we would set it to 64. Now what happens when I say do show IP route? We'll take a look at the routing table first here. And where is that OSPF learned route? It's here. And you can see that the cost is now 65. And give me a second here. There we go. Sorry, I took OSPF a second. I was like, wait a second. The cost is now 129, but we're no longer going to that 172.16.3.1, right? Right up here where it was 65. Who were we via? Who's the next hop? It's the 3.1. It's router 1. Out which interface? Serial 000. We make the bandwidth change to correspond to the bandwidth change that's been made on router 1 serial 000 interface. And now my cost is 129 to go this direction, right? To come out here and go southbound and then I guess to the left, depending on how you're looking at the west. We'll say headed west, right? But now we're coming this way because 129 is going to be less than what? Do show IP OSPF interface. Oops, sorry. Do show IP OSPF interface. Where is my serial 000? Here it is. And the cost, when I tweak the bandwidth to 64 on a serial interface, and again, if you tweak it to 64, with the default auto cost reference bandwidth on any interface, your cost is going to be 1562, right? And that's with the default auto cost reference bandwidth. Now, would you change the auto cost reference bandwidth? And the answer to that is yes. And the best practice is, and again, I'm going to say, generally speaking, the best practice is you set it to the speed of the fastest link in your environment that's participating in OSPF. And if that's the case, the fastest link in this environment that is running OSPF are these gigabit Ethernet links. So how do you change the auto cost reference bandwidth setting? Well, you go into router OSPF, and actually I don't even know if it's 1. So let's say do show run section router OSPF, and it is router OSPF 1. And you're going to say auto cost reference bandwidth. Now remember, we set the speed to a fractional amount, right? Or we can change the bandwidth of an interface on the interface by using kilobits a second. But remember, here, when we tweak the reference bandwidth, it is set in megabits per second because the default is 100 megabits per second. At the time, that was, I don't want to say it was the fastest because maybe somewhere somebody had a gigabit Ethernet interface going. But at the time, this was considered, 100 megabits per second was considered bleeding edge, right? So the auto cost reference bandwidth is set in megabits per second. And remember, if we wanted to set it to a gigabit per second, a gigabit is how many 100 megabits per second? 1,000 megabits per second is 1 gig. Remember, they go up when we're talking about the megabits, right? And we're moving to the in sort of factors of 10. So 100 megabits per second, a gigabit, 10 gigabit, 100 gigabit, right? They're kind of going up in these increments of 10 when we're talking about megabits per second here for this setting. So that would be, if I do that, let me do this. If I do that and then I say, do show run, pipe it to section router OSPF, and these are always good learning moments here. Where is the setting auto cost reference bandwidth 100? Why is it not in there? Yeah, remember, 99% of the time, the Cisco defaults, and they love to test you on these, the Cisco defaults are not in the running configuration that you would see when you say do show run. So that's why when I enter that command, you don't see anything in the config. That's the default. However, if I enter in this command, not only are we going to see a message telling us something very important for a reason that is very similar to the reason we just discussed here, which is if you set the bandwidth to one setting on one side, you better set it to the same setting on the other side of the link to 64 kilobits per second on both ends, or what do you end up with? Asymmetric routing, right? You end up with asymmetric routing. Now you could, and what asymmetric routing is that the path that the traffic takes to get to a destination is different than the path it takes to get back to the original destination. So the path that it takes from the source to the destination, and let me change my color here real briefly to green because I like, and yeah, we'll go yellow. The path that the traffic takes to get to the destination is going to be different than the path that the return traffic flows. And when we had 64 kilobits a second set here, but not set here, the yellow line, that was our flow of traffic. Now, could you make the argument that asymmetric routing is not a bad thing? Sure. What would the use case be? Maybe you want all traffic from this LAN segment to come across this link for whatever reason, because the internet traffic is more important, right? And the internet traffic, or let's say the internet traffic, I would say something like, yeah, we want it to be asymmetric because I just want all of this LAN's traffic to come through the slower link, because maybe these are users that I don't care about, right? Again, you can see I'm kind of struggling to come up with a reason in this topology to say we would love asymmetric routing. We would only set 64 kilobits a second here and then not set it here on the other side of the link when this link is a 64 kilobit per second link. So again, that's asymmetric routing. Is it a bad thing? Well, it depends, right? It really depends. And in this case, it would be if this is a 64 kilobit per second link and we didn't set that here on that interface on router 2. It would be a bad thing. So that is the same conversation we're about to have when I say autocost reference bandwidth 1000. And there's the message I warned you was going to pop up, that you're going to see when you set the autocost reference bandwidth to something other than the default value, which is 100 megabits per second. We just set it to 1000 megabits per second, which is 1 gigabit per second. So it says, please ensure reference bandwidth is consistent across all routers. Well, why does that matter? Why can't I just set the autocost reference bandwidth here and be done with it? Well, there's two very important reasons. The first is that the autocost reference bandwidth, as I've already explained, the metric values are locally, or I should say the interface cost values are locally calculated based on what? Yeah, the reference bandwidth. So now what we have is we have router 2 calculating its link costs on from an OSPF perspective based on a reference bandwidth of 1000 megabits a second. So it's no longer using this equation of 10 to the 8 divided by bits per second. It's using 1000 megabits per second, a gigabit per second. In fact, I actually think I have the text showing me here. Was that it? No, I think this was, or yeah, and so here it is. We set it to a gigabit per second, which is going to be, what is that, a billion? 1,000, 100,000, millions, a billion. So it's going to be 1 billion bits per second. So let's transition back to our drawing, and we can easily check this, right? Do show IP interface, IP OSPF interface. And take a look. The gigabit link speed didn't change. And we wouldn't anticipate that it would change, because when we're saying that the cost is a billion bits per, when the calculation is being run not on 100 million, but a billion bits per second divided by the interface speed, which is a billion bits per second, a billion divided by a billion is 1. But where is that not going to be the case? Well, let's take a look here at serial 001. The cost is now 647, right? And you might be asking yourself, wait a second, can that be right? Well, remember, this interface 001 on router 2 and then 000 are the same, right? You can see that they're the same. But what happened here was, and let me double check something real quick here. Did I set do show run interface serial 000? Oh, and it do show run. And I'm looking for, yeah, so the bandwidth is set to 64 on both sides, right? So let's pull the calculator up. And now what we would say is 1 billion. So 1, 2, 3, 1, 2, 3, 1, 2, 3. A billion divided by 64,000 bits per second. So a billion bits a second divided by 64,000 bits a second gives me what? It gives me this value. And so let's see here if we're waiting for, and it does not look like we're getting the value that we would anticipate on that serial interface that we just tweaked. Because what we should be seeing, and it should match up, is we should see 156.25. And let me do this here. Let me say do clear IP OSPF proc. I was going to say cost, but we want proc. And we'll say yes. It's going to take OSPF down. There we go. It's going to take OSPF down on all the interfaces. It's going to bring it back up. And again, this may be a limitation here of packet tracer. We're going to find out shortly. So show IP OSPF interface. And did it change? It did not change. So it seems like we're tapped out here at 647. Where could I test this? On real Cisco iOS. I'm going to leave that drawing stuff there for just a second. So here, show IP OSPF interface. And if you look, I could actually give the specific interface. So I could say interface fast Ethernet 00.816 is what we're interested in. Sorry, did it twice there. Did not mean to expand that out. There we go. And so I see only that interface. Well, what is the cost of that interface? Well, it's a fast Ethernet interface. The auto cost reference bandwidth is the same as fast Ethernet. So 100 million divided by 100 million is 1. That's why our cost is 1. Let's tweak this. Let's go into global config, interface fast Ethernet 00.816, and let's say bandwidth 64. Again, something you're probably not going to do, but I'm doing this so that we can see that the cost is going to change. Now say do show IP OSPF interface fast Ethernet 00.816. Now what is my cost? Aha, the cost is 1562 when we're using the default auto cost reference bandwidth. Remember, what should it be? It should be 15,625. Here it's 1,562. Well, what are we missing? Let's go into router OSPF and let's say router OSPF. I believe it's 1. Give me a second here. Do show IP, do show run, and section router OSPF. Let's make sure it is 1. It's 10. It's a good thing we looked. So router OSPF 10, auto cost, reference bandwidth, 1,000 to make it a gigabit per second. And it's telling me you better make that consistent across all routers in your area, because right now router 8 is the only router who is calculating the per interface cost using a reference bandwidth of 1,000 megabits per second, 1 billion bits per second, which means this router, and I'm trying to get to my do show IP OSPF interface that better work for me, and there it is. So the packet tracer limitation, not a big deal, but this proves to you that the cost, when the auto cost reference bandwidth is set to a gigabit per second, all of the interface costs locally on that router are now being calculated in a different fashion with a different equation. Now we're dividing 1 billion bits per second by the bits per second on the interface. Instead of dividing by 100 million, we're dividing by 1 billion. And so this router and its outgoing interface costs to reach other networks has now changed. And as you can see, again, it's an inverse relationship. The faster the bandwidth, right, the lower the cost. However, here we lowered the bandwidth down to 64. And that is what drove the cost up. It's that inverse relationship between bandwidth and cost. So now router 2 is the only router who is using this new formula locally to assign costs to its OSPF interfaces of 1 billion bits per second divided by the interface speed in bits per second. And we would want that to be the same across all the routers. And this is router OSPF 1. This isn't just a best practice. This is mandatory. You want to do this, right? It's beyond a best practice that you would not want to go into an environment and start setting the auto cost reference bandwidth to different values on different routers. Again, could you find some corner case? I'm sure that you could, but that is not what you would probably be doing. And so we come to each of the routers here, and we are going to go into router OSPF 1, auto cost, reference bandwidth. Sorry about that. And we want 1,000. And now it is consistent across all the routers in your OSPF routing domain. Now, the final thing I'm going to say is this. You need to be careful. If you have slower 64 kilobit per second links, and in the same domain, you have 10 gigabit per second interfaces, you could run into the exact same problem that we had with all of the higher links looking the same from a cost perspective, if you came into this environment and said auto cost, and here we'll do it, and we're going to have to do it over here, and I'll clear the screen now because we're going to have to do it over here. If on this router I said auto cost, reference bandwidth, and remember, this is set in megabits per second, so that's 100 megabits, a gigabit, that's 10 gig per second, because we have a few 10 gigabit per second links. And I hit enter, and you can see, ensure that that is consistent across all routers. But I'm more concerned about what now, and now I can actually do this, where I'm going to include, I just want to see that one, I want to see the line with cost. So, sorry, I forgot to put include. So now, what is my cost? Well, that's a very, very important field, right? Or that's a very important value. Because if this is a 64 kilobit per second, again, we're suspending reality and we're saying that, hey, we have a 64 kilobit per second link, and the cost is $65,535. Well, what if on that interface fast Ethernet 00.816, what if on that interface, it's actually not 64 kilobits per second, it's 128 kilobits per second. Now what happens to the cost? Gee, that's funny. That looks like the same cost to me. And it is. And so now we have the reverse issue, where before we had super fast interfaces, gigabit, 10 gig, 40 gig, 100 gig, but the auto cost reference bandwidth was defaulted to 100 megabits, making all those fast interfaces look the same. Here we have the reverse problem, where we have maybe a few 64 kilobit per second links, slow links, and we've got some 10 gig interfaces, and you watch my video and you said, oh yeah, always set the auto cost reference bandwidth to the speed of whatever the fastest interface in that network is going to be. Recognize that this is what you're going to run into. What if I set the bandwidth on that interface, let's say it's 256 kilobits per second? There's the break-off point, right? So if you had a whole bunch of 64, let's say you have a whole bunch of 64 kilobit per second links, and you have a whole bunch of 128 kilobit per second links, old serials, fractionals, whatever, and they're in the same routing domain, where you've got 10 gig interfaces that are running, and you set the auto cost reference bandwidth to 10 gigabits per second, recognize that your 64 kilobit per second links and your 128 kilobit per second links are now being treated by OSPF with the same cost. And that might be a problem. Now, if this is the case, how do you fix that? What's one way you might be able to address this? Well, one way, if the fastest link was 10 gig and you set it to 10 gig, maybe you could throttle it back. But remember, this is us tweaking the bandwidth. The real way to do it would be to go under the interface and change the IP OSPF cost of the individual interface. And here's where we're going to wrap up. Again, this is another sort of argument for, unless that is the actual bandwidth of the interface, 64 kilobits per second, do not come under the interface and put in bandwidth 64 trying to manipulate the routing, right? So let's say that this is 64 kilobits per second. Excuse me, or that it's not 64 kilobits per second. And again, we're going to lose the 100 on the activity. Who cares, right? It's more important that we get this aspect of things down. And I'm going to say bandwidth 1544. We're going to set it back to what it was, right? Conf T. And we're going to say that this is interface serial 000, bandwidth 1544. And so we set it back to the default setting of the interface. Do show int serial 000. And what is our bandwidth? It's 1544. Now on router 1, which path would I be taking And let me back up here and let me in and out of here. And let's just say show IP route. Which path am I taking to get to the 172.16.2? Bingo, I'm going out my serial 000 interface. Now, why is the cost 648? And this is okay, right? This is okay because we use the auto cost reference bandwidth of 1,000. That is still on these routers, and that is legit because that is the fastest link speed that we have. But what if your manager comes to you and says, hey, I know that we've got full T1s here, right? And I'll just say T1 for 1.544 megabits per second. We've got full T1s between all these routers, but I don't want traffic going over this link. But we're running EIGRP, we're running quality of service. You can't manipulate it with bandwidth because that's going to screw all that up too. Just for the OSPF traffic from PC1 out to the internet, and from PC1 to PC2, and from PC2 back to PC1, I want all traffic to go 132 for PC1, and for PC2, I want it to go 231. So I don't want any asymmetric routing. In OSPF, make that happen for me. Well, we already know that the total cost is 648 from router 1's perspective to come here and go here. All I would have to do is make the cost setting on that interface worse than if I go here and here and out. And so how could we calculate that? And again, how do you calculate that without actually like going onto the interface and putting a whole bunch of values, just waiting for OSPF to change the path and go 132 for PC1 to go router 1, router 3, router 2? Well, I already showed you how to calculate this. Show IP OSPF interface. So what's my cost right now out the serial 001? Okay, the cost is 647. So, and I was going to, excuse me. So my cost, and I don't want yellow, sorry about that. We're going to go back to red here. So my cost is 647. All right, so coming this way, it's going to be 647. Now remember, and that's out this interface. Now, what's my cost coming out that interface? Because we're going this way. Well, it's a serial link. It's going to be the same. The auto cost reference bandwidth is the same. And now you see why that is important. So the cost is 647. And then the cost of this interface, the gig interface, even though the reference bandwidth is a gig, that just means it's now 1. So it's going to be 647 plus 647 plus 1. And so that's going to be, and here's where my math is going to fail me. It's going to be 5. I'm going to add the 1 in. I'll say it's 648 plus 647. We're going to add the 1 in right away. So 648 plus 647 would be 5, 9. And I'm assuming my math is correct here. So it should be 1295. In fact, I am terrible at math, which is why I like the calculator app. So 648 plus 647, 1295. So if I know that the cost out this interface, right, that the cost of that interface is 647, the cost is going to be 648, and the cost going this way is 1295, all I would have to do is set the cost here on the serial 00 interface so that going this direction looks better. Meaning, what if I set it to 1295 on that interface right there? Because if it's 1295 plus 1 is 1296. So let's get into interface serial 000, and let's say IP OSPF cost, and let me prove to you, if I set it to 1293, we should not have a change. From router 1's perspective, we should not have a change. Do show IP route. And in fact, do show IP route. And let me see if it'll let me do this. 172.16.2.0. In this, I say show IP route. It shows me everything. I only am interested in seeing information beautiful for this route. And let's hope that the beautiful statement holds up. And there it is. The route metric is 1294. going the bottom, right, the southbound and then northbound is going to end up to be $12.95 to get to that network, that route. The cost of that route is $12.94 going northbound right away, router 1 to router 2. And we see that because right here is the next hop IP. That asterisk meaning that is the next hop. The candidate next hop is the 172.16.3.2. That is router 2. And it's because the cost is still less to go straight away router 1 to router 2 than it is to go router 1 to router 3 to router 2. But let's change that right now. What if I say IP OSPF cost $12.95? And again, remember, the cost of that interface, not the whole path, that interface. So it would be $12.95 plus 1 is $12.96. So I should be able to say IP OSPF cost $12.95, hit enter, do the show IP route for that specific network, and yes, the new best metric is $12.95 going to who? The new candidate next hop, router 3. So now what do we have to deal with still? Absolutely, we have asymmetric routing, because PC2 is still going to immediately go down to router. It's going to go to router 2, its default gateway, and then it's going to come down to router 1, and then it's going to go out to PC1. So how would we fix this? Just like the bandwidth conversation we had. If you're performing layer 3 traffic engineering and you're manipulating the flow of traffic in a layer 3 domain, like OSPF, and you don't want asymmetric routing, let me say that, and you didn't desire asymmetric routing, for whatever reason, you want to make sure that both sides of that segment have the same cost value set, so that traffic that transits through one way, when it goes to come back, is going to be treated the same way. So we would come here, get into interface serial 000, and say IP OSPF cost $12.95. And let's now come to PC2. Let's now rerun that trace route. And where do we go? We go out to router 3, down to router 1, and over to PC1. And so we've gotten rid of asymmetric routing. So let's catch our breath here. Let's take a step back. We have covered an incredible amount of what I would consider to be advanced OSPF features and layer 3 traffic engineering. We looked at how the cost is calculated. We manipulated it every which way from Sunday. We got onto a real Cisco router, saw the reverse issue that you could run into if you had a bunch of really fast links, but still had some legacy links. And we talked about why you would not want to use bandwidth to do this traffic engineering. You want to use the bandwidth when that is the speed of that interface. That's when you put the bandwidth statement on there, not when you're performing layer 3 traffic engineering. Again, because it impacts other things. All right. Well, I think we've gone long enough on this activity. Thank you guys so much for watching. I hope this has cleared up a lot of questions that you might have had about traffic engineering, about advanced features, about the bandwidth setting, about the auto cost reference bandwidth, excuse me, and about how to avoid asymmetric routing when you are doing layer 3 traffic engineering. All right. Thank you guys so much for watching. Hope this has helped you out, and I hope to see you in the next video.